Something pulled. The hour is late enough that the body has started making its own decisions. The shoulders have dropped. The jaw has unclenched without you asking it to. Something in the middle of the chest has gone soft. There is a version of this, of the particular loosening that happens when you stop being in charge of yourself, that feels like being pulled down, not falling, pulled, as if something beneath the floor has a very mild, very patient interest in you. It does. You have never once felt the magnetic field. This is one of those facts that sounds dramatic when you first encounter it, and then, very quickly, just becomes strange in a quieter way. You have lived your entire life inside something that is doing something to the space around you, orienting every loose iron fleck in the room, bending the path of charged particles arriving from the sun, keeping certain things out that would otherwise come in. And you have felt none of it. Not a hum, not a weight, not the slightest pressure on the back of the hand. Some animals feel it, or something near it. The mechanism is still being worked out. For you, nothing. And yet, here is the thing about invisible forces. The not feeling them is not the same as them not mattering. Gravity does not feel like anything either. You only notice it when you step off something. The atmosphere doesn't feel like much until the day it isn't there. The magnetic field is in that category, the category of things that the body has never had to report on, because they have never, in the history of bodies, failed. They are working on that. The field comes from below. That is where to start, not with the compass, not with the North Pole, not with the maps, but with the fact that the planet is generating something continuously right now as you breathe, as the shoulder relaxes another fraction of an inch into the surface beneath it, as the thought you were about to have dissolves before it formed. The core of the earth is iron, two parts of it. The inner core is solid and roughly the size of the moon, and it is about 5,000 degrees, which puts it somewhere near the surface temperature of the sun. The outer core surrounds it. The outer core is also iron, but liquid. Liquid in the way that water is liquid, except at pressures so immense that the comparison starts to lose its usefulness fairly quickly. This outer liquid iron is moving, slowly by some measures, not slowly by others. It is conducting electricity as it moves, because iron conducts electricity, and a moving conductor in a magnetic field, which the outer core is already inside of, generates more magnetic field, which drives more movement, which generates more field. This is called the geodynamo. The name makes it sound like a piece of equipment. It is not a piece of equipment. It is a planetary scale process that has been running with occasional interruptions for most of the Earth's 4.5 billion years. It has no switch. It has no manual. It has, as far as anyone can tell, no interest in remaining stable. A compass needle is a small bar magnet. When you hold a compass level, the needle aligns with the horizontal component of the magnetic field at that location. What the needle is doing, technically, is minimizing its own energy. It rotates until the forces on it balance. It points where it points because pointing there costs it the least. This is true of a lot of things. The direction it settles on is not the geographic North Pole, which is the point where the Earth's rotational axis meets the surface. It is the magnetic North Pole, which is a different location, one defined by where the field lines go vertical, where, if you could stand there with a compass that moved freely in 3 dimensions instead of 2, the needle would point straight down into the ground. These two poles have never been in the same place. The angular difference between them, measured from any given location on Earth, is called magnetic declination. Every map that uses a north arrow has to account for it. Every compass user who wants to navigate accurately has to know it for their region. Every navigation system built before satellite positioning had to be corrected for it constantly, and not by a fixed amount, because the correction is different in different places and also different at different times, because the magnetic pole moves. It has always moved. For most of the 20th century, the North Magnetic Pole was drifting, mostly across the Canadian Arctic, at somewhere between 0 and 15 kilometers a year. Patient, predictable enough to update the charts every few years and consider the matter handled. Navigators learned to apply the declination correction for their area. Airports repainted numbers on runways. Runway designations are based on compass bearings, rounded to the nearest 10 degrees. Occasionally, when a pole shift made the designation inaccurate, a small administrative inconvenience, a professional footnote. Sometime around the 1990s, the drift began to change. By the early 2000s, it had accelerated. By the 2010s, the pole was moving at speeds approaching 60 kilometers per year, roughly 4 times faster than it had moved for most of the century before. It crossed from Canadian territory into international waters, then continued toward Siberia, and has continued moving in that direction since. 60 kilometers per year does not sound fast. It is fast. The World Magnetic Model, a joint product of the United States National Oceanic and Atmospheric Administration and the British Geological Survey, updated on a 5-year cycle, had to be updated early in 2019, before the scheduled revision window, because the pole had moved far enough that the existing model had drifted outside acceptable error margins for navigation. This had never happened before in the model's history. What changed? The leading explanation involves something happening inside the outer core, in those two vast regions of magnetic influence moving beneath the surface, one sitting roughly under Canada, one under Siberia. These structures are not stable. The Canadian one has been weakening. The Siberian one has been, by some measures, gaining relative influence. The pole, caught between them, has been moving toward the stronger pull. Imagine 2 people pulling on a rope. Now imagine the one on the left getting gradually tired. That is a simplification. The actual dynamics are in 3 dimensions, operating across thousands of kilometers of liquid iron, driven by temperature gradients and rotation, and forces that interact in ways that require some of the most complex fluid dynamics models in existence to approximate. But the pulling sensation is real. The pole goes where the field takes it. The body does not register any of this. The field is roughly 25 to 65 microteslas at the surface, depending on location. That number is very small compared to a refrigerator magnet. It is enough to move a needle. It is not enough to move anything you can feel, but it is enough to keep certain things out. The sun is constantly shedding material, a stream of charged particles called the solar wind, moving at between 300 and 800 kilometers per second, more or less continuously. When it reaches Earth, most of it is deflected by the magnetic field before it can reach the atmosphere. The field acts as a kind of extended boundary, pressing outward into space, diverting the incoming stream around the planet. Without this, the solar wind would interact directly with the upper atmosphere. Over geological time, this appears to be what happened to Mars, which lost most of its atmosphere and whatever liquid water it once had. Mars has no active geodynamo. Its global magnetic field collapsed billions of years ago. The solar wind has been working on its atmosphere since. The Earth's surface stays habitable in part because of the process running inside the outer core right now, as the iron churns and the field holds its rough shape above us. Here is something to sit with before the next chapter. There is a spot above the South Atlantic where the field dips lower than it does anywhere else, not uniformly, but in a broad region stretching from roughly South America across the ocean toward Africa. This is called the South Atlantic Anomaly. Satellites passing through it receive higher radiation doses than they do anywhere else. Some satellites are put into a kind of standby mode as they cross through it, to protect instruments from the extra bombardment. The anomaly appears to be related to the weakening happening in the field beneath that region. It has been growing slowly for decades. Some researchers think it may eventually split into two distinct anomalies. No one is certain what happens next. The needle points, not where it always has, but it points. And the pulling, which you cannot feel and have never felt, continues below you, through the floor, through the many miles of rock, into the liquid iron moving in the dark at temperatures the word hot was not built to carry. Something has a mild, patient interest in the charged particles overhead. It is still holding the inside of a planet. You cannot enter. Start here, inside the iron, not in the ground, not in the crust, which is the thin rind we live on, only 30 kilometers thick at its thickest continental points, practically nothing by the standards of what sits below it. Not in the upper mantle, where the rock is technically solid but behaves, over millions of years, like something that has forgotten what being rigid feels like. Deeper, past the lower mantle, past the point where pressure has squeezed every pocket of space out of the mineral lattice, past the boundary that geophysicists call the core mantle boundary, which sits about 2,900 kilometers below the surface and marks the edge of something the rest of the planet does not resemble. Here the iron begins. The outer core is liquid iron, and, to a lesser extent, nickel, along with lighter elements like sulfur, oxygen and silicon that have dissolved into the mix over geological time. It extends from roughly 2,900 kilometers depth down to about 5,100 kilometers. That is a shell of liquid metal more than 2,000 kilometers thick. If you could pull the Earth apart like an orange and hold the outer core by itself, it would be larger than Mars. It is somewhere between 4,000 and 6,000 degrees down here, depending on where in the outer core you are standing, which you are not, and cannot be, and will not be. The pressure is between 100 and 300 gigapascals. 1 gigapascal is roughly 10,000 times the atmospheric pressure at sea level. At 300 gigapascals, the numbers stop being useful to imagine. What you can say is that the material is behaving in ways that the same iron on the surface would not recognize as related to itself, and yet it flows. The flowing is slow by the standards of anything you have ever watched move, and fast by the standards of what it is flowing through and around. The estimated velocity of bulk flow in the outer core is somewhere in the range of tens of kilometers per year, in the fastest observed regions. This is not slow. The tectonic plates at the surface move at a few centimeters per year. The outer core is moving 1,000 times faster than the ground you're sitting on. Quietly, without announcement, the iron beneath you is going somewhere. The motion is driven by several things working together in ways that are easier to list than to separate. Heat. First, the inner core is hot, and it is releasing heat outward into the outer core fluid, which rises because hot fluid is less dense, which displaces cooler fluid, which sinks, which is heated in turn. This is convection, the same process happening in a pot of water on a stove, at temperatures the pot could not survive and scales the stove could not approach. And there is compositional buoyancy as well. The inner core is very slowly growing, crystallizing iron out of the liquid at its surface and releasing lighter elements back into the outer core fluid, which changes the fluid's density locally and drives its own patterns of circulation. And there is the Coriolis effect, the influence of the Earth's rotation on moving fluids, which twists the convective columns into organized structures aligned roughly parallel to the planet's rotation axis. These three things, thermal convection, compositional buoyancy, Coriolis deflection, stir the outer core together in patterns that are, to put it plainly, not yet fully understood. The models improve, the full picture is not there yet. Now, the inner core, solid, roughly 1,200 kilometers in radius. At its center, the pressure reaches somewhere around 360 gigapascals. The temperature is probably around 5,000 to 6,000 degrees Celsius, a number which sits near the surface temperature of the Sun, and which the solid state of the iron there still surprises researchers when they stop to think about it. Iron is solid there not because it is cool, but because the pressure is so great that even at those temperatures, the iron cannot maintain the extra volume that the liquid phase would require. The inner core is also rotating. This was discovered by analyzing seismic waves produced by large earthquakes that travel through the Earth's center. Because iron crystals in the inner core are not randomly arranged, seismic waves travel through the inner core at slightly different speeds depending on their direction relative to the crystal alignment. By comparing wave travel times from earthquakes occurring at different points on the globe, seismologists determined in the 1990s that the inner core appears to rotate at a slightly different rate than the mantle and crust above it. The differential is small, perhaps between 0 and 1 degree per year faster than the surface, though the precise value has been debated back and forth with each new analysis. But the inner core is, in some sense, its own object with its own rotation, nested inside the rest of the planet like a thought inside a thought. Everything here is moving in relation to everything else. The inner core turns at its own rate. The outer core fluid flows in column-like structures shaped by Coriolis forces. The mantle above creeps and convects over millions of years. The cross slides and accumulates and subducts and lifts. None of these motions are synchronized. The magnetic field emerges from the misalignment as much as from the materials themselves. It is the motion of the conducting liquid iron through an existing weak field that amplifies and sustains the field, a process called the dynamo effect, in which kinetic energy is converted into magnetic energy. The field feeds the motion feeds the field. Neither is the original cause of the other, or both are depending on where in the cycle you enter. This is not a metaphor. This is the geodynamo, a feedback process, running continuously, self-sustaining within limits, capable of being disrupted by changes in the flow patterns that drive it, which are themselves influenced by the field it produces. The liquid iron does not know it is doing this. Going outward now, slowly, from the core mantle boundary upward through the mantle, through the crust, through the ocean floors, through the atmosphere, the field that was generated 2,900 kilometers below you has propagated out through all of that and into space. It has not changed nature by doing so. It is still lines of force, still a dipole shape roughly resembling the field you would get from a bar magnet at the center of the Earth, tilted about 11 degrees from the rotation axis, extending outward until it meets the solar wind on the sun-facing side at roughly 10 Earth radii, 64,000 kilometers from the surface, where the field pressure and the solar wind pressure roughly balance, and the boundary called the magnetopause is established. The field has come a long way from where the iron is. And here is the thing about that journey. The field that arrives at the surface is not a clean recording of what the core is doing. It is modified by currents in the mantle, by the magnetism of the crustal rocks, by electrical currents in the ionosphere above. What the compass needle reads is a composite of all of these, dominated by the core field but shaped at the edges by layers and layers of additional signal. Separating them out is one of the ongoing technical projects of geomagnetic science. The iron at the center does not know about any of this complexity. It flows because it must. The field follows because the field has no other option. Inside the outer core, right now, while the jaw rests and the eyes are almost closed and the room has gone to that deep quiet it finds after midnight, the iron is going somewhere. The columns are turning. The lighter elements are rising. The inner core is crystallizing another fraction of a millimeter. It has been doing this since before there was anything alive on the surface to not feel it. What the rocks remember. The volcano has already gone quiet. That is when it matters. The lava cools, slowly, in the geological sense. What looked like destruction becomes, over days and weeks, a new surface. Something settles. Inside the cooling rock, something else happens. Certain minerals contain iron. Magnetite, for instance. Iron oxide, common in basaltic lava. When the lava is fluid and hot, the magnetic domains within these minerals are disordered. They point in different directions. They cancel each other out. The rock has no net magnetism to speak of. Then the temperature drops. There is a threshold, different for different minerals, around 580 degrees Celsius for magnetite, called the Curie point. Below it, thermal energy no longer has enough force to keep the magnetic domains in constant agitation. They settle, they align with whatever ambient magnetic field is present at that exact moment of cooling. Then the rock solidifies around them, and the alignment is locked. The mineral does not forget. It cannot forget. The physical structure of the crystal lattice holds the domain orientation in place, as rigidly as anything in the natural world holds anything. Short of reheating the rock above its Curie point again, or applying a sufficiently strong external field, the magnetization recorded at that moment of cooling will remain. This is called thermoremnant magnetization. The name arrived and then was released, and now what matters is the thing the name describes: rock that remembers. The ocean floors record the field the way a slow tape recorder records a sound, laying down strips of new basalt on either side of the mid-ocean ridges as the seafloor spreads. The ridge is where the plates pull apart. Lava wells up into the gap, cools, and records the direction of the magnetic field at that moment. Then the seafloor moves outward, carrying its recorded direction with it, and new lava fills the gap, recording the field at the next moment. What you get, if you tow a magnetometer behind a research vessel over these ridges, is a striped pattern. Bands of rock magnetized in one direction, bands magnetized in the opposite direction, alternating symmetric on either side of the ridge, spreading outward across the ocean floor. Each stripe is a chapter. Each boundary between stripes is a moment in time when the magnetic field reversed, when north became south, and south became north, and the compasses, had there been compasses, would have pointed the other way. The stripes were first noticed in the late 1950s and early 1960s, and their interpretation was one of the key pieces of evidence that established the reality of seafloor spreading and, by extension, plate tectonics. The reversals were real. They were recorded. They were in the rock everywhere the ocean floors had been surveyed. The field had been doing this for a very long time. Sitting with that for a moment. The reversals are not small corrections. They are not adjustments. The entire global field, the same field currently holding the solar wind at bay, the same field the compass needle is pointing into right now, has flipped. The north magnetic pole became the south magnetic pole. The lines of force that currently arc outward from the geographic north region and return near the geographic south, bowing through the magnetosphere and back, those lines reverse direction completely. This happened while life existed on Earth. It happened many times while life existed on Earth. Hundreds of times. The species alive during those reversals did not, as far as the fossil record can determine, notice in any catastrophic way. This is either reassuring or strange, depending on what you were expecting. Perhaps both. The duration of a reversal, the transition period during which the field is actively reconfiguring, is estimated from the rock record at somewhere between 1,000 and 10,000 years. Long in human terms, very fast in geological ones. During the transition, the field weakened significantly, possibly to as little as 10% of its typical strength in some models, though this number is not precisely known. The field becomes multipolar, not simply reversed, but complex and fragmented, with multiple north and south poles scattered across the surface. It wanders, it searches, and then it settles into the new direction, and the record continues. The ocean floor holds all of this, striped, quiet. The rock does not know what it recorded. A crystal locked its domains into alignment on a day, or decade. That has no other witnesses. There was no atmosphere yet. There were no observers. There was only the cooling and the field, and the moment the two of them met inside the mineral lattice. The record is more complete than most records. It goes back tens of millions of years. The seafloor being recycled by subduction puts an upper limit on how far back the ocean floor record runs. The oldest ocean floor is only about 200 million years old because older seafloor has been swallowed back into the mantle. But terrestrial rocks can supplement this. Certain lake sediments record field direction through a similar process as magnetic particles settle and align in the sediment column. Ice cores carry different records. The stratigraphy of the reversal history, the geomagnetic polarity timescale, has been pieced together from dozens of sources and now extends with reasonable reliability across tens of millions of years. The last reversal was about 780,000 years ago. It is called the Matuyama-Brunhes boundary, named for the two polarity epochs it separates. Before that boundary, reversed. After it, and continuing to now, normal polarity, meaning north magnetic pole near geographic north more or less. 780,000 years is a long time. It is also not infinite. The average interval between reversals over the past several million years has been somewhere between 200,000 and 300,000 years. There is no strict periodicity. Reversals do not happen on a schedule, and the intervals vary enormously, from under 100,000 years to several million years without a reversal. But the average is there, and we are past it. This is noted in the literature without alarm. The rock waits, the ocean floor spreads, the stripes continue outward from the ridge, carrying their silent record into waters where no one is measuring. Something is cooling. Something, right now at this moment, somewhere on a mid-ocean ridge, is crossing the Curie point and locking in the field as it currently is. That record will still be there in 5 million years. The rock does not forget. The map that was always wrong. Begin far away. Begin with the problem of knowing where you are, not philosophically, practically. You are on a ship. The year's anywhere in several centuries before 1960. The choice of century does not matter as much as you might think, because the problem is the same in all of them. You're on a ship and you're not near any coast you recognize, and you need to know where you are, and the tools available to you are a sextant, a clock, and a compass. The sextant and the clock together give you latitude and longitude. Latitude from the angle of the sun or a known star above the horizon. Longitude from the difference between local solar time and a reference time kept by the clock. Every 4 minutes of difference is 1 degree of longitude, and a good clock can keep the reference time accurate enough over weeks that the calculation is reliable. These two instruments, working together, can place you on the surface of the Earth to within a few miles. They are elegant, they work. The compass tells you which direction you are heading. And here is the quiet problem that navigators have understood in various degrees of precision since at least the 15th century. The compass does not point to the geographic north. It points to the magnetic north, and the magnetic north is not on the map where geographic north is. It is elsewhere. It is elsewhere by a number of degrees that depends on where on Earth you are standing. And that number is not constant. It changes as you move, and it changes over time as the pole moves, even if you stay still. This difference between the direction the compass points and the direction of true geographic north is called declination. The word itself is old. The awareness of the problem is older than the word. Navigators handled this. They measured it. They recorded it in tables, harbour by harbour, for coastlines they traded along regularly. Edmund Halley, the same Halley for whom the comet is named, sailed 2 voyages in the late 1690s and early 1700s, specifically to measure magnetic declination across the Atlantic Ocean and produce a chart of isogonic lines connecting points of equal declination. His chart was not perfectly accurate. No chart of this kind can be perfectly accurate, because the field does not sit still long enough for a comprehensive survey to capture it whole. But it was the first systematic attempt to map the invisible and the shape of the project, measuring the field broadly enough to see its large-scale structure, has defined geomagnetic science ever since. The specific challenge that Halley was orbiting, without quite naming it, is that declination is different everywhere and changes over time everywhere, and both of these facts are caused by the same underlying reality. The magnetic pole is not a fixed point. It is a location in motion. The map is a snapshot of a moving target. The moment the survey ends, the chart begins to age. This is not a problem that better instruments solve. This is a problem that is built into the nature of what is being measured. The world magnetic model exists because this problem never went away. It only grew more consequential. Modern navigation, aircraft, ships, military systems, civilian smartphones, depends on knowing the magnetic declination to acceptable accuracy, and acceptable accuracy for a commercial airliner is tighter than acceptable accuracy for a 15th century trading vessel. And the magnetic pole is moving faster now than it was during most of the 20th century, which means the snapshot ages faster. The model is updated every 5 years. It is a mathematical description of the global magnetic field, a spherical harmonic expansion, which is a way of describing a field that varies smoothly across a sphere, by decomposing it into simpler component shapes that add together. The model is fitted to actual measurements from ground-based magnetometer stations, from ships and aircraft surveys, and from satellites. Most recently from the European Space Agency's Swarm constellation, 3 satellites launched in 2013 specifically to measure the magnetic field with high spatial and temporal resolution. The output of all this measurement is a set of numbers, coefficients in the spherical harmonic expansion, that together describe the field well enough for navigation purposes. The description is not perfect. The field has small-scale features that the model smooths over. The field also changes faster in some places than others. The model handles the average rate of change. When the rate of change in a particular region exceeds what the model predicted, the model's accuracy in that region degrades faster than expected. This is what happened in 2018 and 2019. The pole was accelerating. The model was aging faster than the 5-year update cycle could keep up with. The early update was issued. What the orbit of this chapter keeps returning to is the following. The map assumes a world that agrees to hold still long enough to be mapped. The magnetic world does not agree to this. It has never agreed. It agreed less than usual in the late 20th century, and less still in the early 21st, and no one is sure what it has agreed to since. There is a moment. It happens to navigators who know enough to think about it, when the instrument in the hand and the chart on the table are both accurate and still tell different stories, because the chart captured the field in a year that is not this year, and the field has moved on. The instrument is honest. The chart is honest about a different moment. This is not a failure of either. It is a feature of trying to describe something that does not stop. Halley's isogonic chart, wrong as it was even at the moment of printing, still helped. Wrong maps help. The question is not whether the map is right. The question is how fast it is getting wronger. The pole went where the iron told it to go. The chart went out of date. The navigators corrected for this, as navigators always have, as quietly and professionally as people who have learned to live with a flaw that is very slowly tilting and have decided on balance that this is manageable, and that managing it is simply part of the work, and that the ship moves forward regardless, into water that is not on any chart yet, toward a north that is not where any north has been before, under a sky that is carrying invisibly the field that makes the needle move, which is to say, the field that makes any of this possible, which is to say, the field from the iron, from the convection, from the depth, from a process that has never once paused to let anyone catch up with it. Reversals. The field is in the middle of doing something right now, at this moment, and it has been in the middle of doing it for several thousand years, and it may be in the middle of doing it for several thousand more, and whether what it is doing constitutes the beginning of something much larger, or simply a long fluctuation that resolves back toward normal, that is genuinely not known. This is not a hedge. This is the state of the research. What is known, the Earth's magnetic field, has reversed before. This has been established through the rock record, through the ocean floor stripes, through dated volcanic sequences on land, through lake sediment cores taken from sites across multiple continents. The reversal history is a real thing, documented, cross-checked, debated at the level of specific dates and durations, but not at the level of whether it happened. It happened. Hundreds of times. The field flipped, north became south, south became north, and then the field ran in the new direction until the next reversal. The last one was the Matuyama-Brunhes boundary, 780,000 years ago. A geologically recent event, a humanly unimaginable span of time. There have also been events called excursions, shorter, less complete episodes in which the field weakened significantly, and the poles wandered far from their usual positions but did not complete a full reversal. The most studied of these is the Lachamps excursion, which occurred roughly 42,000 years ago. During the Lachamps, the field dropped to somewhere between 0 and 6% of its current strength over a period of centuries, with the poles briefly occupying positions near the equator before recovering and returning to roughly normal polarity. This happened during the Upper Paleolithic. There were modern humans alive. The evidence suggests the weakened field allowed significantly more cosmic radiation to reach the Earth's surface and atmosphere, with effects that are still being researched. Now expand outward from that. A full reversal is not a switch being flipped. It is more like, and this comparison is not quite right, but it is closer than most. It is more like watching something very large that has been moving in one direction gradually lose confidence in that direction, slow, stop for what seems like a very long time, and then begin moving the other way, erratically at first, finding its structure in a new direction, stabilizing. During the transition, the field is not simply reversed, it is disorganized. The dipole that currently dominates, the roughly bar magnet shape with one magnetic north and one magnetic south, weakens significantly, and the higher order components of the field, the ones that are usually masked by the dominant dipole, become relatively more important. Multiple magnetic poles can exist simultaneously. Their positions move rapidly, by geomagnetic standards, across the surface. The overall strength of the field during this period is estimated to drop to somewhere between 10 and 25% of its typical interreversal value. though the estimates vary by study and location. Lower field strength means reduced shielding. Reduced shielding means more of the solar wind's energy reaches the upper atmosphere. More energetic particles reach the surface at lower latitudes than they typically would. The ozone layer, maintained partly by a chemical balance that is sensitive to high-energy particle bombardment, may be affected. The aurora, typically confined to high latitudes, extends toward the equator. The radiation environment at the surface changes. None of this, in the fossil record, has produced a clear extinction event associated with a reversal. This has been checked. The reversal boundaries in the rock record do not consistently align with mass extinction horizons. This is either evidence that the biological effects were too diffuse and slow to register as sharp events, or that the field's protective role, while real, is not as catastrophically necessary as the dramatic language sometimes used around this topic might suggest, or that the biological record simply does not preserve the right kinds of effects at the right resolution. Probably some combination of all three, and contract. Back to the present field, back to what is actually being measured now. The overall strength of the Earth's magnetic field has been declining. This has been observed since the earliest systematic measurements, which begin with Carl Friedrich Gauss in the 1830s. Since then, the field strength has decreased by roughly 10%. 10% in under 200 years is, by geomagnetic standards, fast. The South Atlantic anomaly, the weak region above the South Atlantic that satellites cross with caution, is a surface expression of something happening in the deep field beneath it. Studies of the field at the core mantle boundary suggest there is a large patch of reverse flux beneath the southern Atlantic and the southern tip of Africa, a region where the field at the core boundary is oriented opposite to the main field. This reverse flux patch has been growing and intensifying, and it is thought to be a significant driver of both the overall field weakening and the anomaly at the surface. Some researchers consider this a sign that a reversal may be in early stages. Others consider it a fluctuation within the normal variability of the field, which has varied considerably over historical and archaeological timescales without reversing. The honest answer is that distinguishing between these two possibilities, the beginning of something large versus a recoverable dip, requires data from timescales longer than we have been measuring, and the field has a history of behaving ambiguously right up until it doesn't. Expand again. The Lachance excursion, 42,000 years ago, Cooper et al. In a 2021 paper in Science, analysed the effects of the Lachance event using a combination of ice core data, tree ring records, and cave deposits. They proposed that the dramatic weakening of the field during this period significantly increased atmospheric ionization, altered climate patterns, and may have contributed to the extinction of the megafauna in Australia and the disappearance of the Neanderthal population in Europe. Though this interpretation has been debated, and the causal chain is difficult to establish at this resolution. What is less debated is that the Lachance weakening changed the chemistry of the atmosphere. Radiocarbon production spiked because more cosmic rays were reaching the lower atmosphere. This shows up clearly in radiocarbon records and in cave deposits. The field change left a chemical signature in the air. The air recorded it. The rock recorded it. The ice recorded it. When the field is weak, the world shows it in ways the world keeps. The field right now is weakening. It has been weakening for at least 180 years of direct measurement. The south magnetic pole has been moving. The north magnetic pole has been accelerating. The South Atlantic anomaly is growing. Whether this is the beginning of a reversal or an excursion or a fluctuation that will recover within a few thousand years is something that cannot be known from the inside. This is the honest situation. The people studying this have access to the best instruments ever built for this purpose, and to a rock record stretching back hundreds of millions of years, and to satellite data of unprecedented resolution, and the answer they arrive at is, we cannot yet tell. The pulse of this chapter has been expanding and contracting, because that is what the evidence does. It goes outward to the historical record, which shows that this has happened before and life continued. It comes back to the present measurements, which show change at rates that are unusual. It goes outward to the physics, which says that a weakened field means more exposure. It comes back to the data, which says the field is still there, still functional, still holding most of what it has always held. The field weakens, the field searches, perhaps the field settles, perhaps it does not. The 780,000 years since the last reversal has no opinion on whether it will continue. What can be said is that the process is running. What cannot be said is where it is going. These are two different kinds of knowledge. Both are available. Only one of them arrives at night in a way that allows sleep. And yet here we are, and the sleeping is still possible, and the field is still measurably there. Faster now. Something changed. The question is when. The data shows a drift. Patient, slow, continuous. A pole moving across the Canadian Arctic for most of the 20th century, its position updated every 5 years in the charts, its speed unremarkable. Then, not unremarkable. The North Magnetic Pole's position has been tracked with reasonable precision since the first expedition to locate it, by James Clark Ross in 1831. Ross planted a flag on the Boothia Peninsula in what is now northern Canada, and noted that his compass pointed straight down into the ground. He had found the pole. It was at roughly 70 degrees north, 96 degrees west. By 1904, when Roald Amundsen located it during his Northwest Passage voyage, the pole had moved roughly 50 kilometers. By the time of the next major expedition, in 1948, it had moved further, still within Canadian territory, still moving at a speed that would not have alarmed anyone checking the charts. The speed through the mid-20th century was in the range of 10 to 15 kilometers per year. The pole crossed the surface the way a ship crosses a large lake. Consistently, in a roughly consistent direction, at a speed that could be plotted and projected and trusted within reasonable margins. Then, in the 1990s, the speed increased. By the 2000s, it was moving at closer to 50 kilometers per year. By the 2010s, some years brought movement of nearly 60 kilometers. The pole crossed into international waters north of Canada. It moved past 85 degrees north, within a few degrees of the geographic North Pole. It has continued towards Siberia since. Why the 1990s? Why not the 1970s or the 2020s? Nobody is entirely sure. The thread to follow is this. The acceleration of the surface pole is connected to changes in the flow patterns of liquid iron in the outer core, which are themselves connected to the competition between two large-scale magnetic flux concentrations sitting beneath Canada and Siberia respectively. The Canadian flux patch has been weakening since at least the 1980s, and possibly earlier. The Siberian flux patch has been intensifying, or at minimum, the balance between them has been shifting. The pole is drawn toward the stronger region, the way a ball in a shallow bowl is drawn toward the lowest point. The bowl's shape has been changing. The ball has been responding. The timing of the acceleration does not have a clean explanation for why it began when it did. The outer core dynamics operate on timescales of years to decades, with shorter fluctuations superimposed. The acceleration may have been building for longer than the surface measurements showed, with the signal becoming clear only when the cumulative effect exceeded the background noise, or something changed in the flow patterns in the 1980s and 1990s that propagated to the surface as an acceleration in the subsequent years. The models suggest the latter is more likely, but the models are constrained by the quality of data below the core mantle boundary, which is limited. There is a feeling, reading this literature, a feeling familiar to anyone who has learned something new about a process they thought was settled, of the floor turning out to be not quite where you thought it was, not a dramatic drop, a small correction, a revision to the depth. The speed matters practically. The faster the pole moves, the faster the magnetic declination changes at every point on Earth beneath its path. Northern Canada and Alaska have experienced some of the largest declination changes in recent decades. Places where the compass correction that was accurate in 2000 was measurably wrong by 2015, and measurably wrong again by 2020 in the opposite direction from the expected drift. This is the bodily part. The compass is not broken. The ground has not moved. The stars are where they always were. But the direction the needle points has drifted silently without announcement, while everything else appeared to hold still. For most purposes, this is absorbed by GPS and satellite navigation, which do not depend on the magnetic field. The practical consequence falls on systems that still use magnetic heading as a primary or backup. Certain aircraft systems, certain ship systems, certain military applications, certain emergency navigation protocols. And there is one other group for whom the movement of the pole is not a technical abstraction, the birds, but that is for another chapter. What the thread ends on is this: the acceleration is real, is measured, is published, and has not shown clear signs of stopping. The pole has been moving fast for 3 decades now. Whether the speed plateaus, increases further, or gradually decreases as the flux competition beneath the surface evolves into a new equilibrium, these outcomes are currently indistinguishable from the available data. The speed the pole is moving right now, at this moment tonight, is roughly 40 to 50 kilometers per year, which is to say, while you have been listening to this chapter, while the body has been settling into its horizontal state and the breath has been coming slower, the magnetic North Pole has moved. The needle in every compass has a slightly different target than it had a few hours ago, and the iron below has gone somewhere it has not been before, and there is no map for it yet, and the map that will eventually be made will already be wrong by the time it is finished. This is the situation with the pole. It has always been moving. It is now moving faster. The threshold crossed sometime in the 1990s, and the world went through it without noticing, and has been on the other side since. Canada, Siberia, and the disagreement between blobs. 2,900 kilometers below the surface, two enormous structures sit in the liquid iron of the outer core like weather systems that have been stalled for decades, one beneath the North American continent, one roughly beneath Siberia and the Russian Arctic, and the word beneath here is doing significant work, because neither is beneath those places the way a foundation is beneath a building, but rather the way a dream is beneath waking, which is to say, related, caused by the same source, but not geometrically connected in any way you could walk along. These structures are not visible, they were inferred. The inferring began seriously with satellite data. Ground-based magnetometers can measure the field at specific points on the surface, but they cannot distinguish cleanly between the field contribution from the core, the field contribution from crustal rocks, and the field contribution from ionospheric currents above. To see the core field clearly, you need to be above the crust but below the ionosphere, in low Earth orbit, which is where the Ørsted satellite was placed in 1999, and where the CHAMP satellite operated from 2000 to 2010, and where the SWARM constellation has been operating since 2013. From those orbits, with instruments sensitive enough to detect changes in field strength of less than a nanotesla, the large-scale structure of the core field has been mapped with a resolution that was not previously achievable. What the mapping revealed was a field that, at the core mantle boundary, has regions of concentrated magnetic flux, places where the field lines enter and exit the core with much higher density than the surrounding areas. These patches of concentrated flux are not uniformly distributed. They cluster at certain latitudes and longitudes, and their positions and intensities change over time. Two of these flux concentrations in the Northern Hemisphere have been the primary anchors of the North Magnetic Pole. The surface pole sits above the resultant of their combined influence. When both are roughly equal, the pole sits between them. When one is stronger, the pole moves toward it. The Canadian patch has been weakening. Slower now. Just that sentence. Just let it sit. The Siberian patch has been relatively stable, or intensifying slightly. The balance has shifted. The pole, which spent most of the 20th century sitting closer to the Canadian patch's influence, has been walking toward the Siberian one. The walk became a jog sometime in the 1990s. The question of why the Canadian patch is weakening gets into the dynamics of liquid iron convection in a way that is not fully settled. There are suggestions that a plume of upwelling hot fluid beneath the core mantle boundary in the Atlantic region, related to the same deep dynamics that may drive the South Atlantic anomaly, is disrupting the flux concentration that maintained the Canadian patch. Hot upwelling iron carries magnetic field lines upward with it, and can scatter concentrated flux patches into a broader, weaker distribution. This is a hypothesis that is consistent with the data and with the physics. It is not yet confirmed. The outer core is not accessible. The inference runs through the surface measurements backward, through layers of mathematical modelling to an educated description of what the flow must look like to produce the field signatures observed. The spatial picture is worth holding for a moment. 2,900 kilometers down, the outer core's surface, the boundary between liquid iron and solid mantle, is not smooth in any magnetic sense. It has regions of intense flux, regions of weak flux, and regions of reverse flux where the field direction at the boundary is opposite to the global main field. These reverse flux patches sit primarily beneath the southern hemisphere and significantly beneath the South Atlantic. The combination of weakening forward flux in the north and growing reverse flux in the south contributes to the overall weakening of the dipole component of the global field. The picture at the boundary is not static. It changes on timescales of years to decades. The patches grow, weaken, drift, and interact. The north magnetic pole on the surface tracks the changing balance of the northern patches, but the whole field is responding to a much more complex dance happening across the entire core mantle boundary simultaneously. The field we experience at the surface is the averaged, smoothed, integrated result of all of this. Every contour on a geomagnetic chart is a kind of summary. Behind it is the full complexity of what is happening 2,900 kilometers down. Complexity that the summary is useful for navigators, but that hides, as all useful summaries do, everything that is actually going on. The two blobs are not the whole story. They are the chapter of the story that is most relevant to the moving pole, but the outer core is a global structure, and what happens under Canada and Siberia is continuous with what happens under the Pacific and under Antarctica and under the Indian Ocean. The full field is a single thing. The blobs are a way of talking about features within that single thing that happen to matter most for the question of where north is. There is something in this configuration, the idea of a direction defined by the contest between two distant invisible structures, neither of which has any knowledge of the compass that is trying to read them, that feels like it should be more dramatic than it is. But it is not dramatic. It is slow. It is patient. It is iron flowing because it is hot and rotating, and the patterns that emerge from that flowing happen to produce a field that happens to have a north, and the north happens to be moving because the pattern is changing, and the pattern is changing because that is what patterns in liquid iron do. The pole is where it is because the iron made it so. The iron has made a new arrangement. The pole is following. The weak place, yes. Start with a satellite, not any particular one. One of several hundred objects in low Earth orbit circling the planet at roughly 500 to 600 kilometers altitude, completing an orbit every 90 minutes or so, doing whatever it was sent up to do, relaying communications, observing weather systems, measuring ocean temperatures, mapping agricultural land use. Most of the time, the satellite operates without incident. Its instruments collect data, its transmitters send, its solar panels charge its batteries, its operators on the ground receive telemetry, note that all systems are nominal, and move on to the next task. Then the satellite crosses a particular region of its orbit. The region is above the South Atlantic, stretching roughly from the coastline of South America around the Rio de la Plata region, across the ocean toward the African continent. As the satellite enters this region, something changes. The radiation environment changes. The flux of energetic charged particles hitting the satellite increases substantially, by factors of between 2 and 1,000, depending on altitude and what exactly is being measured. Memory errors increase. Single event upsets, moments when a cosmic ray or energetic proton flips a bit in a memory register, become more common. Some satellites enter a protective mode, shutting down non-essential systems, closing apertures, conserving resources, waiting to cross the region before resuming normal operations. The region has a name. It is called the South Atlantic Anomaly. From 500 kilometers, the anomaly is a practical problem. Come closer to the surface, to where the field lines run through the upper atmosphere, and the anomaly is a structural feature of the global field, a place where the lines of force are closer to the Earth than they are anywhere else, where the lowest boundary of the Van Allen radiation belts dips down to altitudes that satellites regularly cross. Come closer still to the surface itself, and the anomaly is a weak spot in the field. The magnetic field strength over the South Atlantic is measurably lower than it is at equivalent latitudes elsewhere. At the surface, roughly centered on the anomaly, the field strength is less than half of what it is at comparable latitudes in the Northern Hemisphere. This dip in the field corresponds to a region of concentrated reverse flux at the core mantle boundary below, a place where the field at the deep boundary is oriented opposite to the main dipole. The field above a reverse flux patch is locally weakened. The Van Allen belts drop lower, cosmic radiation penetrates deeper, satellites malfunction. The anomaly has been known since the earliest satellite missions, and likely earlier. Anomalous compass readings in the South Atlantic were noted by navigators for centuries, though the cause was not understood. It appears in the geomagnetic record going back at least several centuries. What has changed is not its existence, but its size and intensity. The anomaly is growing. In terms of surface area, it has expanded over the past century. The minimum field strength within the anomaly has decreased, and there are recent studies, based on satellite data from the Swarm constellation, suggesting that the anomaly may be developing a secondary minimum to the west of the primary one, a feature that, if it persists, could indicate the anomaly is in the process of splitting into two distinct weak regions. Whether this represents the beginning of something larger, a precursor to a reversal or excursion, or a recoverable fluctuation in the deep field is, as with so much of geomagnetism, genuinely uncertain. The reverse flux patch driving the anomaly has been observed to grow and drift. It has not stabilized. The radiation environment at the surface, under the anomaly, is not clinically dangerous to human beings who live in the region beneath it. The atmosphere provides substantial shielding. The anomaly is a concern for systems operating outside the atmospheric shield. Satellites, spacecraft, high-altitude aircraft on transpolar routes that occasionally cross the anomaly's edges. Astronauts on the International Space Station, whose orbit regularly passes through the anomaly's edge, experience elevated radiation exposure during those crossings. NASA monitors this and schedules extravehicular activities to minimize exposure. For the people living in South America and the South Atlantic, the anomaly is invisible. It has no sensation. The field does what it does. The particles that do penetrate are absorbed by the atmosphere and the body's ordinary repair mechanisms, and the average person living in Buenos Aires or Cape Town is not thinking about what is happening 2,900 kilometers below them or 500 kilometers above them. This is fine. It should be fine. It is fine. And yet the fact that something is not perceived is not the same as the fact that it is not there, and the anomaly is there, and it is growing, and the sky above the South Atlantic is a little thinner than it was, and a little thinner than it was before that. Zoom to the smallest detail of this. A single proton travelling at a significant fraction of the speed of light ejected from the sun days ago as part of the ordinary continuous solar wind. It has travelled 150 million kilometres through interplanetary space. It reaches the Earth. At almost every point on Earth, the magnetic field curves its path around the planet. The field exerts a force on the moving charged particle, perpendicular to its direction of travel, and the particle follows a curved arc that carries it away from the atmosphere and around the Earth. Over the South Atlantic, the field line it is following dips lower than it would elsewhere. The altitude at which the field is strong enough to deflect particles of this energy is lower here. The proton continues its path. The atmosphere begins at roughly 100 kilometers altitude. The proton reaches the atmosphere. It collides with an oxygen or nitrogen molecule. A cascade of secondary particles follows: pions, muons, electrons, photons, each carrying a fraction of the original energy, each potentially interacting with further molecules. This is not unusual. This happens everywhere, continuously, at a background rate. Over the anomaly, it happens more. The particle does not know it has crossed into a different region. The field line it followed had no marking. The weak place has no edge you would notice from the inside. Animals that know. The bird is already in the air. It has been in the air for several hours. Below it, somewhere, the landscape is changing from the familiar to the unfamiliar. The trees thinning, the rivers rearranging, the smells shifting in a way the bird may or may not register. What the bird is doing, as it has been doing for hours and will continue doing for hours more, is navigating, crossing a distance, finding a place it has never been to in this particular body, but that something in its nervous system recognizes as a destination. How it does this is not fully settled. There is a component of avian navigation that appears to be magnetic. The evidence for this has accumulated since the 1960s, when experimental work by Wolfgang Wiltschko and others demonstrated that European robins in migratory orientation showed consistent directional preferences that shifted when the ambient magnetic field was experimentally altered. The field was changed, the birds changed direction. Put the field back, the birds put their direction back. Since then, the evidence has expanded and complicated. Different species appear to use different mechanisms, possibly multiple mechanisms simultaneously. The magnetic sense in birds is not understood the way vision is understood. There is no bird magnetoreceptor that has been cleanly isolated, agreed upon by the field, and fully characterized. There are candidates, 2 of them. The first is the radical pair mechanism. In the eye, specifically in certain photoreceptor cells, in a protein called cryptochrome, incoming light may trigger chemical reactions that produce pairs of molecules with unpaired electrons. The magnetic field influences the spin states of these unpaired electrons, which influences the ratio of reaction products, which influences the bird's visual experience in ways that may encode directional information. In this model, the bird experiences the magnetic field through a subtle modification of what it sees, not as a separate sensation, but as a tint, a gradient, a something in the visual field that carries directional meaning. The bird might see north as a difference in the way the light looks rather than as a felt pull. The second is magnetite-based sensing. Magnetite crystals, the same iron oxide that records field direction in cooling lava, have been found in the beak tissue of some bird species. These crystals, aligned with the field, could in principle act as a kind of mechanical compass, transmitting force through nerve cells when the bird changes orientation relative to the field. Whether this mechanism is functional for navigation, or whether the magnetite serves another purpose, or whether it is a vestigial remnant, the research is ongoing, and the answer is genuinely not settled. What is settled is the behavior. Migratory birds navigate. The field appears to be one of the things they navigate by. When the field is disrupted by geomagnetic storms, by strong local magnetic anomalies, by experimental manipulation, the birds sometimes go wrong. Not always, not catastrophically. But directional errors increase. Individuals that would normally arrive accurately sometimes arrive off course. Some do not arrive at all, though attributing any specific absence to magnetic disruption specifically rather than to weather, predation, or 1,000 other variables is difficult. The drift of this chapter keeps coming back to the same thing without pressing it. The birds are using a feature of the world that is changing. The field that they have, over evolutionary time, learn to read or learn to feel or learn to see is moving. The corridors that were accurate for their ancestors are shifting. The signpost is relocating. Whether this matters for bird migration at the current rate of field change is not clearly established. Birds' magnetic orientation appears to be learned and calibrated during early life, not simply inherited as a fixed reading. If the calibration updates with the field, which some research suggests is possible, then a slow drift of the pole might be absorbed without significant navigational cost. The system updates, the bird recalibrates, but the drift is not slow anymore. There are other animals, sea turtles, salmon, spiny lobsters, sharks, certain insects. The magnetic sense has been found, or strongly suggested, in many species, using many different mechanisms. Not a single solution, but many solutions to the same problem, arrived at independently across evolutionary lineages, which means the problem was worth solving, which means the magnetic field has been a reliable enough feature of the world for long enough that investing cognitive and structural resources in reading it paid off for the animals that did. The field has been reliable. It has been reliable for millions of years, across hundreds of speciation events, across the evolutionary emergence of flight and of long-distance migration, and of the specific navigational challenges those things create. It is now changing faster than it has for most of the time those animals have been navigating it. The salmon that finds the river mouth it was born in, locating it partly by chemical cues and partly by magnetic ones, following a map that is encoded in its nervous system over years of development, that salmon is navigating toward a coordinate that has shifted. The chemical map is stable. The magnetic map has drifted. Something in the combination may be less accurate than it was. Maybe not. Maybe the margins are comfortable enough. Maybe the redundancy in the system is sufficient. Maybe the river is far enough south of the main region of field change that the practical difference is small. The honest version is, we don't know yet. The field is changing. The animals use the field, and the downstream effects of that combination on population-level navigation accuracy, on breeding success, on range, are something the research is working toward and has not yet fully described. The bird is still in the air. The sun has moved since the chapter started. The bird is still going the direction it was going. It may be precisely right. It may be carrying a version of north that is slightly out of date. It cannot tell the difference between a correct map and an outdated one. Neither from the outside can anyone watching it. The wings move. The direction holds. Below the bird, the landscape continues its slow shift from familiar to unfamiliar. Somewhere ahead, there is a destination. Whether the destination is exactly where the field is pointing, whether the field is pointing where it used to point, these are questions the bird is not asking, and that the research has not yet answered, and the bird keeps flying regardless, guided by something it cannot describe and that we cannot fully see, through a field that the iron below is quietly rearranging. The last chapter has no argument. Something has just finished. Not the field, not the chapter before this one, not the drift, which is still ongoing, still measurable, still making its quiet way across the Arctic towards Siberia at a pace that produces no sound and no sensation and no evidence that anything is happening except the numbers, which are changing. What has just finished is the accumulation of things said. The field is not broken. That needs to be said plainly, once, and then it can be released. The field is weaker than it was 2 centuries ago when systematic measurement began. It is weaker by roughly 10%. The pole is moving faster than it moved for most of the century before this one. The South Atlantic anomaly is growing. The reverse flux patches at the core mantle boundary are intensifying. All of this is real, measured, published. The field is still there. It is still deflecting the solar wind. It is still curving the paths of charged particles above the atmosphere. It is still sustaining the radiation belts that concentrate the particles it cannot fully deflect. It is still making the needle move. Everything it has always done, it is still doing. The situation is one of change, not failure. These are different situations. They call for different responses. They settle differently in the body at midnight when the distinction finally arrives. There is a way this story could have been told, is told in some places, as a crisis narrative. The field is weakening, the pole is accelerating, the South Atlantic anomaly is growing. A reversal may be beginning. The satellites are failing. The birds are lost. This version is not dishonest about the facts. The facts are the same. What is dishonest is the implied timescale and the implied consequence. The weakening, the acceleration, the anomaly. These are happening at rates that matter for navigation systems and satellite operators and long-term infrastructure planning. They are not happening at rates that matter for the air you breathe tonight, or the atmosphere you will breathe tomorrow, or the atmosphere that will exist in any human lifetime. The honest version is less convenient in either direction. It is not reassuring in the simple sense, because the change is real, and some of its consequences are already being managed. It is not alarming in the simple sense, because the timescales involved are long, the variability in the historical record is large, and the field has done versions of this before without ending anything. The honest version is this. The iron in the outer core is in a different configuration than it was 100 years ago. The pattern of its flow has shifted. The balance between the flux patches under Canada and Siberia has changed. The dipole has weakened, the pole has moved. Whether these changes are part of a recovery fluctuation that will stabilize within a few thousand years, or the early stages of a polarity excursion like the Lachance event 42,000 years ago, or the beginning of a full reversal, these scenarios are currently indistinguishable from the inside, from where we are, from this moment in the process. The rock will know eventually. The ocean floor is recording this right now, at the spreading ridges where lava is cooling and locking in the field direction as it currently is. In a million years, the record will show what this period was. The stripe will be in the stone. Whether it is a stripe of normal polarity that continued, or the beginning of a transition stripe, or a thin anomalous band that represents a brief excursion, the rock will hold that. We will not be here to read it. The rock does not need us to be. There is a small fact that belongs at the end of this. The solar cycle affects the magnetic field slightly. During periods of high solar activity, solar maximum, which occurs roughly every 11 years, the increased solar wind pressure pushes the magnetopause closer to Earth on the sun-facing side. Geomagnetic storms become more frequent. The auroras extend further toward the equator. This is a short cycle fluctuation superimposed on the long cycle drift of the core field. Both are happening simultaneously. The solar maximum makes the field dynamic over timescales of days. The core dynamics make the field dynamic over timescales of centuries and millennia. The geologic reversal history makes the field dynamic over timescales of hundreds of thousands of years. All of these are the same field. The same lines of force that curve above the oceans and dip toward the poles and protect the atmosphere and move the compass needle are the same ones being pushed inward by the solar wind, being generated by the iron convection, being reversed over geological time, being read by the birds and by the sailors and by the satellites, and by the occasional person lying still enough at the right hour to feel, if not the field itself, at least the shape of the thought that the field makes possible. The needle points. It is pointing somewhere new, somewhere it has not pointed in living memory, or in historical memory, or in any memory that a human kept. The iron made a new arrangement, slowly, over the past several decades, and the arrangement is still being made, and the needle is following the arrangement the way the needle always follows, the way all of this has always followed. Iron and field and force and motion in a loop that has no beginning anyone has found. The thought settles, not completely, not with the clean click of something resolved. It settles the way sediment settles, still in motion at the smallest scale, still slightly uncertain about where the bottom is, but down, lower, resting on something that was there before it, and will be there after. The room has been quiet for some time. The chest has been rising and falling at its own pace. The shoulders are where they went an hour ago. Below all of this, through the floor and through the rock and through the mantle and through the boundary into the liquid iron, something is still moving. Something is always still moving. And the needle, very far above it, in the dark of a drawer or hanging from a lanyard or folded into the lid of a hiking kit that has not been opened since last summer, the needle is pointing. It does not know it is pointing. It points because pointing costs it the least. Whether what it is pointing at is what it has always pointed at, whether the destination the needle has been faithful to for all the time there have been needles is still the destination, that is a question the field has not answered yet. The iron is still working on it. Below the floor, below the rock, in the dark and the heat and the pressure, the iron is still working on it. That is where this ends. Not because the answer is there, because that is where the question lives.